Okay, so now we're working into our section 4.3, the Venn diagram perspective on probability. Before we can actually get into Venn diagrams, though, we're going to be talking about an associated mathematical concept that's going to help us talk more rigorously about what Venn diagrams do and how they work to help us calculate probabilities. So imagine you have this pool of people or collection of items, and you separate them into groups, not necessarily of equal size, but you want to make sure that everybody fits into one of those subgroups, and that no person can be in more than one of these groups at once. So for illustration's sake, I have a oblong object here that's separated into 4 distinct categories: A1, A2, A3, and A4. And any person that we select from our sample or population is going to fit into one of those groups. Real-world examples include things such as race, age, employment status, where there's some qualifiers that we need there in order for it to be so that every person fits into one of these groups or not. So formally, though, what a partition is, so this is the formal definition, is we suppose we have some set A1, A2, up through AN, where N is just the number of subdivisions that we want for our group. So if we want 10 groups, that's 10. So these are going to be subsets of this larger set S. And importantly, there are 2 conditions or characteristics for a partition. The first is that each pair, A sub I and A sub j, where I is not equal to j, all that means, by the way, is that these are 2 distinct subgroups in our set of subgroups, but the I and j are just placeholders. They're just dummy variables. So each pair that are not the same, they need to be disjoint. In other words, their intersection, so A sub I intersect A sub j, is the empty set. There's nothing that it belongs to both. This is a condition that we also sometimes call pairwise disjointness. So whenever you hear that condition, that's what we're talking about. And it can be shown, we don't need to talk about it in any detail, but it can be shown that all of these groups, if we take all of their intersections at once, or any combination of the intersections at once, they're also going to be empty. So literally there's no way to group these into larger groups such that there's any overlap in any place. So literally what we're saying with condition 1 is no overlap ever. 2 is that S is equal to the union of all these subgroups. So it's equal to A1, union A2, union blah, 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 union N. So this condition we also say A sub 1 through A sub n, that these sets cover S. So think of it like a blanket, right? You don't want any, straggly bits that's not covered by the blanket. So these 4 pieces, they in the picture, they cover the group. Or you can think of it like a jigsaw, right? So a jigsaw puzzle. Each piece, right, doesn't overlap, and they connect and cover the entire image. So as an example, let's consider this set S of participants in a clinical study. So S is going to be our larger group, right, the picture. And now we're going to designate a few of these subgroups, which are the jigsaws themselves. So let A sub 1 equal the group of people that are aged 0 through 9. A sub 2 is the people that are aged 10 through 19. A sub 3 is the group of people aged 20 through 29, and so on until we get through the group of people that are aged 90 to 99. And we're going to suppose that nobody in this group is older than 100 years old, or the 99, I should say. So it should be clear now that any person in this group S, any participant in this clinical study, is going to fit into one of these categories and only one. So nobody is, aged -3. Nobody is aged 19.5. We're talking about we're strictly talking about integers, whole numbers. And nobody can belong to two at once, right? Somebody who's 19.5, we're not saying that. We're saying they're either 19 or they're 20. So they're either in A2 or in A3, and they're not in any other category, just one at a time. This is a good example of a partition, so we're partitioning by age. The reason why we need these tools is because Venn diagrams actually use partitions. And with partitions, it's really nice because we're going to be able to calculate probabilities much more easily, in that when these pairs are disjoint and you want to figure out the probability of the union, it's actually a simple application of what we're going to call the addition rule. And the addition rule works a lot better when there's no overlap.